Ever wondered why molecules aren't just random blobs? I mean, they're the building blocks of literally everything, but they have these really specific, predictable 3D shapes. And that shape is everything. It dictates how a molecule behaves, what it does, even what it smells like. The reason behind it all is actually surprisingly simple, and that's exactly what we're going to break down right now. Okay, so check this out. On the left, we've got carbon dioxide, CO2. It's a perfectly straight line. On the right, sulfur dioxide, SO2. Now, at a glance, you'd think they'd be pretty much the same, right? One atom in the middle, two on the sides. But sulfur dioxide is obviously not a straight line. It's bent. So, that's our big mystery for today. Why? They both have 3 atoms, but their shapes are totally different. What's the hidden rule here that forces one to be straight and the other one to bend? Let's figure it out. The secret is a really powerful idea in chemistry called VSEPR theory. Now, the full name is a mouthful, valence shell electron pair repulsion, but the idea itself is super simple. Think about it. The groups of electrons around that central atom all have a negative charge. And what do negative charges do? They push each other away. They all want their own personal space. And the final 3D shape of a molecule is just the result of them getting as far away from each other as they possibly can. Now, in VSEPR theory, we basically look at 2 types of these electron areas, or domains. First, you have bonding pairs. These are the electrons that are actually forming the connections, the chemical bonds, between atoms. Then you have non-bonding pairs, which you'll often hear called lone pairs. These guys are electrons that just hang out on the central atom, not involved in any bonds. And here is the absolute key, the most important part of this whole thing. Not all repulsion is the same. Those non-bonding lone pairs, they're kind of like the bullies of the molecular world. Because they're not stretched out in a bond, they're held tighter to the central atom. They take up more space, and they push on all the other electrons much, much harder. You have to remember that. It explains everything. So let's start with the easy cases. What happens when a molecule has no lone pairs on its central atom? Well, when all the electron groups are nice, polite bonding pairs, you get these perfect, predictable, totally symmetrical shapes. Think about it. If you've got a central atom with only 2 electron groups pushing away from it, what's the farthest apart they can get? It's simple, right? They go to opposite sides, forming a perfectly straight line. And boom, this takes us right back to our first puzzle piece, carbon dioxide. That central carbon atom has 2 electron domains, those double bonds to the oxygens, and they just push each other to opposite ends of the molecule. That's why it has that perfect linear shape. The angle between the bonds is a perfect 180 degrees. You literally can't get any further apart than that. Okay, what if we add a 3rd electron domain? How do 3 things get as far apart as possible? Well, they spread out into a flat triangle, kind of like a peace sign. We call this shape trigonal planar. Boron trichloride is a textbook example. The boron in the middle is bonded to 3 chlorines. That's 3 bonding domains, no lone pairs, so they all settle into this perfectly flat triangular shape. And the angle between each of those bonds? A perfect 120 degrees. It's just simple, beautiful geometry. All right, now for the big one, 4 electron domains. Now, your first instinct might be to think they'd form a cross, right? Like a plus sign with 90-degree angles. But you have to remember, molecules live in a 3D world. To really get away from each other, they pop out into a 3-dimensional shape that we call a tetrahedron. It's like a pyramid with a triangular base. Methane, CH4, is the classic example here. You've got carbon in the middle, bonded to 4 hydrogen atoms. They don't lie flat. They arrange themselves in this perfect symmetrical tetrahedral shape. And that magic number for the bond angle in a perfect tetrahedron is 109.5 degrees. That's the maximum separation they can get in 3-dimensional space. Okay, so we've seen the perfect, polite, symmetrical shapes. But what happens when we swap out one of those nice bonding pairs for one of those super repulsive lone pair bullies we talked about earlier? This is where it gets really interesting. So let's go back to our starting point, the perfect tetrahedron. 4 electron domains, all of them are bonding pairs, and you have that ideal 109.5-degree angle. Everybody's happy. Now, let's start messing with it. Take a look at ammonia, NH3. The nitrogen in the middle has 4 electron domains in total. 3 are bonded to hydrogens, but 1 is a lone pair. Now, you can't see the lone pair in the final shape of the molecule, but boy, can you feel its effects. It acts like a powerful invisible force field, pushing down on those 3 bonds and squeezing them together. The shape we see is called trigonal pyramidal, and that bond angle gets compressed from 109.5 all the way down to about 107 degrees. The perfect geometry gets distorted. And what about water, H2O? Well, the oxygen also has 4 electron domains. But get this, 2 are bonds to hydrogen, and 2 are powerful lone pairs. With 2 bullies pushing down, the effect is even bigger. They shove those hydrogen bonds even closer together, creating that famous bent shape with an angle of just 104.5 degrees. This is the whole reason that bend exists, a shape that's responsible for pretty much all life on Earth. It's one of the most important shapes in all of biology. Okay, so now you know the rules of the game. Electron groups repel each other, and those lone pairs repel the most. With that knowledge, you can basically predict the shape of almost any simple molecule. So let's quickly walk through how you can do it yourself. It's really just a simple 4-step process. First, you draw the Lewis structure, which is just a map of the electrons. Second, you pinpoint the central atom. Third, and this is the key, you count the number of bonding domains and the number of lone pairs around that central atom. And finally, you use that count to figure out the final shape. Let's try one together really quick. Carbon tetrafluoride, or CF4. Okay, steps 1 and 2, we look at the structure and see carbon is right in the middle. Step 3 is counting. It's connected to 4 fluorine atoms, so that's 4 bonding domains. Now, are there any leftover lone pairs on that central carbon? Nope, 0 non-bonding domains. So if you have 4 bonding domains and 0 lone pairs, what's the shape? It's our perfect, symmetrical tetrahedral. See? The system works. It's that simple. So I'll leave you with a final little puzzle. This is bromine trifluoride. As you can see, it has this weird T shape with an 86.2-degree angle. This strange shape is actually critical for making things like rocket fuel. Now that you know the powerful shape-distorting effect of those lone pair bullies, can you figure out exactly how many bonding domains and non-bonding domains it must have to create this very specific shape? The answer is hiding in the rules we just covered.